Okay, without further ado, let's start the first session. So, to introduce the speaker, we have Keshav and Vani. Keshav is a senior software engineer with Cloudera, and he is into data engineering team here. And he has got keen interest in Docker, Spark, Airflow, Kubernetes, and a lot into big data. And to talk about Vani, she's software engineer in Cloudera, and she has got expertise in big data technologies. She is with the Golang, Apache Spark, and Kubernetes. And the session is for supercharging Spark workloads using GPU in a shared Kubernetes cluster with Yunicorn. A very long topic. I'll repeat. Supercharging Spark workloads using GPU in a shared Kubernetes cluster with Yunicorn. Over to speakers in the Zoom, Keshav and Vani. Please welcome the speakers.
Thank you.
Thank you.
So, sorry for the long name. There were just too many technologies involved, so we couldn't trim it down. Can we share screen? Okay.
All yours.
Thank you. So, hope you can see my screen. Okay. So, yeah, as you are already aware of the topic, so we'll go past that. So this is me, Keshav, and I think we have already been through the intro, so I think we can skip. Moving on. So agenda. We're going to talk about what and why. What's the problem statement we are trying to solve? Then we are going to talk about the technical details that involve in solving these problems. And then we have a short demo. Just a second, getting some pop-up. So then we have a short demo, and then we'll open for questions, but feel free to interrupt and ask questions in the middle of the presentation also. Okay. So the problem statement, what and why. So this graph is from Global Data Sphere, and it shows how the data is growing over the past few years. And if you see, it is growing at 21.6% every single year. And by that means, by 2026, you're going to have around 220 zettabytes of data. Now, to give you a picture of what a zettabyte is, consider an average smartphone stores 100 GB of data. Then you're going to need 10 billion of those devices to store just one zettabyte of data. If you multiply that by 220, then that's a lot of smartphones. So, and consider just 1% of that data is being processed by data engineers, then that is also a whole lot of data to process. And processing data requires compute and other resources. So we're going to look at this problem from two different points of view. One is the data and the infra on which the data is being processed. So first, the data. So as the data increases, the existing ETL pipelines that you have is going to take longer and longer to complete. So if it is taking 30 minutes, what if it takes 6 hours in future? Right? So it's always going to take more time if it has to process more data. So next is, let's say you want to decrease that time. Maybe you can throw in some more CPUs, more RAM, better machines, but that is going to add to your cost. So that's not also that is also not the solution. And throwing in more CPUs and memory is probably not feasible because it's only going to give you a slight benefit, not a whole lot. Then nobody has time to wait. So if it is taking 30 minutes, we might want to bring it down to 15 minutes, not take it to 6 hours. So the second way to look at this is the infra. Any company has multiple divisions within the company. There can be sales, there can be engineering, there can be marketing, and within that you have further divisions. So are you going to provision an individual Kubernetes cluster for each one of these teams? No, because it's going to add to the maintenance cost. You need more and more people on the maintenance side to keep these clusters running. So what you do want is a shared cluster where you can utilize the nodes as much as possible. I mean, you can keep the nodes busy like 80 to 90% all the time. And at the same time, you are providing whatever is needed for each of these teams. Then, but if you host all of these tenants, by tenant, I mean the different teams, then how do you divide the resources so that, nobody's stepping on each other's feet? So the resources given to the sales team is not being utilized by, the other engineering team. So to solve all these problems, we have Spark on Rapids, which is going to accelerate your Spark jobs, and Unicorn, where you're going to use it to divide your pool of resources in a certain way so that you can use a single cluster in a shared fashion that and not stepping on each other's feet. So that's the solution. And now we'll go with some of the techs, and where Vani will jump in with the GPUs on so Rapids stuff. So Vani, over to you.
Thanks, Keshav. Now that we have an overview, let's jump right into the technical details. So first and foremost thing is GPUs. Now, GPU is, of course, the buzzword in the industry today, but let's really understand the why and the how of using GPUs in Spark, and then discuss what results you can expect from using the same. Right. Yeah. So here we have certain, I've given a basic overview. So why would help you in, so of course there's improvement in Spark operations, and also you're able to use a single environment for your entire data pipeline instead of switching between different CPU and GPU servers. The how is answered by Rapids Accelerator, which we'll be discussing. And I'll also be discussing certain experiments that were performed and what results were obtained, which you can expect in your environments as well. So firstly, the why. So GPUs have, of course, transformed ML applications, but it's important to note that machine learning cannot be done in a vacuum. So the steps before data is ready to be fed into a model are equally important. And in the current scenario, this pre-processing takes about 80% of a data scientist's time. So given the parallel nature of data processing tasks, it's only natural that the massively parallel architecture of GPU should be able to accelerate these Spark queries. Another overlooked benefit of running Spark on GPU is the benefit of using a single GPU powered cluster instead of, a separate cluster, which first does the data preparation, and then you transfer the memory to a GPU setup and then perform ML there. So in this new scenario, which is represented by the figure on the right, we propose combining everything in one GPU powered cluster, which will enhance performance by avoiding the penalty of moving data. Now, so you've all been convinced to use GPUs, but that leads to the question of how. And the answer to that is neatly packaged by Spark in a plugin known as Rapids Accelerator. So this Spark Rapids Accelerator is used to accelerate large-scale pipelines using GPUs with absolutely no code change required to the existing setup. So in order to understand how Rapids works, let's first see how Spark executes a query. So data processing frameworks like Spark evaluate structured queries by constructing and optimizing a query plan. So this kind of query plan is represented on the figure on the left with the blue nodes. So in this case, a main Spark query is broken down into subtasks, each of which contribute to finishing the final query. So the Rapids plugin integrates with Spark's query planner and rewrites the data frames in order to evaluate operations that can be accelerated with GPU. So these are represented by the green nodes in the figure on the right. There are certain operations that Spark cannot accelerate to be run on GPU, and these continue to be run on CPU, which is that one blue node there. And then Rapids has a provision for providing these data transfers between the CPU memory and GPU memory to facilitate a smooth transition and allow individual branches to be able to execute, even if it's shared between GPU and CPU in certain cases. Next slide, please. So the benefit of acceleration using Spark Rapids is that it's a transparent acceleration, which essentially means that a user can expect that a Spark application running successfully on the CPU will also run successfully on the Rapids accelerator enabled setup without any kind of change required. Furthermore, there are certain queries which would exhibit the most impressive amount of speedups. This is documented by NVIDIA Spark and has also been seen in practice. For example, there are high cardinality joins, complex group by operations like data cube or rollup, and other complex aggregations. The reason for these queries exhibiting the maximum speedup is that when these queries are broken down into tasks, those tasks are massively enhanced by being run parallelly and in a columnar format, both of which are the pillars of execution in GPU. So let's get into what results you can expect by running GPUs. So firstly, here I'll be talking about an experiment that was performed within NVIDIA itself. In this case, they used the Criteo terabyte public data set to run pre-processing of a DLRM, which is deep learning recommendation model pipeline. So you can see in this graph that for the optimized GPU setup versus the optimized CPU setup, there was an performance improvement in the pre-processing of 43x without a frequency cap, which is a huge benefit, as you can see. So a second experiment that we'll be discussing is one that was conducted internally in Cloudera along with NVIDIA. In this case, we used an NDS benchmark workload, which is essentially an entire suite of TP-CDS queries that are run using Spark SQL. So these queries were chosen because they are well understood by data practitioners and cover a huge range of analytic as well as realistic use cases. So in this plot, we have plotted the results of this experiment. So the first point to note is the overall speed up. So overall speed up is the average speed up over the time it took to run the entire suite of queries. And we saw a 7x increase in the high concurrency GPU versus the best CPU configuration. Another important point to note is that, as you can see in this graph, every single query exhibited some kind of speed up. So there was absolutely no loss of performance in any kind of query. Another very interesting thing is that the maximum speed up that was observed in a single query was like a whopping 15.8x times. So the benefits of GPU are not only limited to performance, but even a cost-benefit analysis returns positive results. So in the experiment that was done in Cloudera, we noticed the cumulative cost reduction of up to 5.2x times after considering what cost was required even for adding GPU hardware into the system. If you'd like to know more, we've linked a real-world success story, which was conducted at IRS, which is the Internal Revenue System of America, using Cloudera and NVIDIA. And you can read more about the impressive speedups they were able to see. We'll be jumping on to the Yunicorn technical details now, so I'll hand over to Keshav.
Thank you, Vani. So now that we know we need to use GPU to accelerate our Spark workloads, but GPUs are expensive and much expensive than CPUs. So we don't want to provision too much of GPUs in multiple clusters. So the solution is to have some GPU nodes and share it across the teams. So that's where Yunicorn comes into the picture. So you have your Kubernetes cluster and you have your default schedule, but that default schedule is is limiting in a way that it was designed for static, stateful workloads. You deploy a microservice and it keeps on running for quite a long time. But in case of your ETL pipelines, you need a lot of resources for a few hours or few minutes. So it's a burst, it's a batch. And for those kind of workloads, Unicorn actually suits the best. So what is Unicorn? Unicorn is a scheduler. It is agnostic to the underlying orchestrator platform. It means that it works with Kubernetes, it works with Yarn also. Then Unicorn has a concept of called application, which is not there in default scheduler. That helps you. Okay, so that helps you. So in case of default scheduler, you just submit a pod, and that pod is considered as one job. But in case of real jobs, you have a bunch of pods to be considered as an application. So all of these together considered as an application from the point of view of Unicorn. Unicorn is multi-tenanted, means your cluster can be divided to be used by multiple of your teams at the same time. It supports on-prem deployment of Kubernetes and cloud-based deployments of all of them. Then it is plugin based. It does not replaces the existing default scheduler. It augments the existing scheduler at certain points of integrations. So you can choose your resources to be scheduled opt in or opt out of the Unicorn scheduler, and your default scheduler will still kick in and schedule your pods. That was the last point. So moving on. So the bunch of features we have. One is workload queuing. So like I was saying, your organization is having internal divisions, as in you have sales team, marketing team. So you can divide one Kubernetes cluster, share it across all of your team. And for each of your team, you can define a queue where you can say this specific team is assigned to this queue and has this much limit in the cluster. And workloads are submitted in these queues. So when they enter these queues, the sorting happens within the queue, whatever is submitted and what is already running in that queue. And based on that, Unicorn decides to either schedule it to some node or queue it. So in case of, if you see the default scheduler, if you have a resource quota on some namespace and you submit a pod which is exceeding the resource quota, then default scheduler will straight away reject that pod. But in case of Unicorn, it will queue it. And when the resources are actually available, it will schedule them on some node. So next important feature is gang scheduling, and it is very important when it comes to Spark jobs. So a Spark job first comes with a driver, and then there are a bunch of executors to run the actual task. So if you, let's say in case of default scheduler, you just schedule your driver, but the driver is sitting there and the Kubernetes cluster doesn't have any extra resource to schedule the executors, then the driver is doing nothing, just sitting there idle, consuming the resources. So the ideal thing would be that schedule this entire application when the resources for the driver and all of it executors are available. So you schedule it at once. So that's where the gang scheduling comes in. And why is it possible? Because we can consider all of these pods as an application Unicorn. So when you submit your application in a queue, then the sorting happens on top of the application. The sorting, the current sorting that is there in default scheduler is on the individual pods. But in this case, the sorting is happening on the entire application. So that application is consisting of one or more pods, not just a single pod. This is a top, it's a high-level architecture of Unicorn. The most important part of Unicorn is the Unicorn core. This part is agnostic to the underlying orchestrator, Kubernetes and Yarn. But so what it understands is the application. So you submit something, everything gets converted to what this guy understands, and then the scheduling, the sorting, everything happens in this. So this is the brain of the Yunicorn. Now you need something to translate those resources to what Yunicorn understands. So for example, in case of Kubernetes cluster, you have pods, but pod is not understood by Yunicorn core. So this Yunicorn scheduler interface is converting those into what Yunicorn understands. It means applications. Then once the, so for example, you're submitting an application, it goes to the shim. Shim understands what is the pod. It sends the request to the Yunicorn scheduler. This interface, it converts into the application which is understood by Yunicorn core. Yunicorn core looks at the queue. It looks at what is already deployed in this queue, and it sees what is the requested resource. And then it sees if it can schedule it. If yes, then what is that exact node where it has to place that pod. Then it sends that response back to the via the schedule interface back to the shim, and the shim is responsible for binding that pod to the actual node in the cluster. Okay, so I was talking about the hierarchy of queues. So if you see this example on the, let me open this. So on this side, on the right side, you have the root. A root actually represents the sum of all the resources that the Kubernetes is managing. Means sum of all the resources on all the nodes, all the sum of CPU, GPU, and memory combined together. This is represented by the root. I can divide that into logical groupings, logical queues, which is data engineering and data science as an example. And then you can further divide into data ingestion and data pipe processing. So there are two kinds of queues here. One is in green and one is in blue. So the green ones are the leaf nodes. That's where the actual scheduling will happen. There's a pod when you place, it won't go to the data engineering. It would go to either data ingestion or data processing. But you can define quotas on each of these levels, and they are recursively honored when the scheduling has to happen. So how these queues are created? So one way is you define them statically. So Yunicorn expects a config map called Yunicorn configs. And then in that config, you can define all these queues in a tree structure upfront and define the quotas on each of these queues, and then create that config map, and then your Yunicorn scheduler picks it up, and then you have the similar structure in your Kubernetes cluster. That is the static queue. Now, what if you want to not do that? Then you can, while creating your namespaces, you can annotate your namespaces in a way where you can mention what is my parent queue and what is my namespace, of course. And then you can mention what is the resource quota needed. So that will automatically create a queue. For example, if I create a namespace under the data engineering, then I can say my parent is data engineering and my namespace is ABC. So it will create data engineering.abc as a node. So that's the dynamic queue, the auto-created queue. Then the resources are actually located at the leaves. Like I said, the placement of the pods are actually happening on these leaf nodes, and the quotas are set on each of these levels, and they are recursively honored. So this is one example where we deal with the real numbers. So it's the same structure as per the last shown here, same structure. So now we have so this root is representing the entire capacity of the cluster. And then we have further divisions. So data engineering is a queue where we have max capacity and guaranteed capacity. So the max is how much you can demand from this queue. So that maximum you can demand 100 GB of RAM, 30 CPUs, and 30 GPU. That's the max you can ask in this queue. So that is, and there is something called guaranteed. That is, no matter what, these things will always be there. At max, you can go to 100, but at least 80 will always be there for you. Anything that is getting scheduled under this data engineering. Now we have divided this further into two different queues, which is data ingestion and data processing. So if you see, it also has max and guaranteed. So max, there is a rule. So max can be less than equal to the max of its parent. So in this case, it is 100. This guy is 40, so which is fine. But this can be 100 if needed. The guaranteed must be, so the sum of guaranteed quota at leave nodes, so 20 plus 60, which is 80, must be less than equal to the guaranteed quota of the parent, so which is exactly equal to 80. So I'm just talking in terms of the RAM, but the same thing is applicable on CPU and GPU also. So this is the cluster, and we have this configuration. So, and we have these two pods scheduled on this data ingestion queue. This first pod is needing 20 GB of RAM, 5 CPUs. The second is 10 GB, 5 CPU, and 5 GPU. So, so the usage is updated. So usage here, and usage here is always updated after once you have the pods scheduled. So the usage is sum of all of the pods which are already running. So right now it's 30 GB of RAM, 10 CPU, and 5 GPU. And same is done all the way to the root. Now, let's say you ask for scheduling another pod which needs 80 GB of RAM and 4 CPUs. But this guy is, there's a max capacity. There's a restriction that it can only, you can only ask for at max 70 GB of RAM. Then this pod will go into, it will be in the pending state. And when something is available, means let's say some pod gets kicked out or some pod finishes in data ingestion pipeline, or you, sorry, so this here it is 80. So this pod can't be scheduled here. So either you increase this to, let's say 80, but 80 is still not there because the max capacity here is 100. Out of that, 30 is still getting used. So we just have 70. Now, either you can schedule for 70 or less, but not more than that. If you do that, it has to wait and wait for the other resources to be freed up. So next we have a demo that combines both of these two. So over to you, Vani.
Thanks, Keshav. Now that we've gone through the technical details, it's time to see the magic of GPUs and Yunicorn in action. So next slide, please. We'll be discussing and showing you the demo on the Cloudera data platform itself. So I'll just take a minute to give an overview of what this platform looks like. So our next-gen platform covers the end-to-end data lifecycle from ingesting, pre-processing data, and then finally to storing it and using it for ML operations. So each of these steps is represented by an individual data service, represented in orange here. And all of these come together and lie in one seamless platform known as the Cloudera data platform. So we have a Cloudera SDX layer, and this layer is responsible for maintaining the security, governance, analytics, and portability of data across these data services, giving you one single source of truth for all your data needs. So there are various form factors supported, such as on-prem, private cloud, hybrid cloud, or multiple public cloud networks. So we'll be focusing on the private cloud platform today to show you the demo. And let's look at, before we jump into the recorded video, we'll look at certain commands, basic kubectl and Spark commands, which are helpful while working with GPUs in a GPU cluster. So here, these commands are useful while managing heterogeneous GPU nodes. And what that refers to is two situations. Either your setup is a GPU plus CPU combined setup, and you would like to specify which worker nodes are running GPUs, which this is how you can do that by adding a node label. So you're clearly, so these are provided by NVIDIA itself, the nvidia.com/GPU, and you're specifying the kind of GPU model that's running here. So the other kind of heterogeneous GPU node setup is when it's all GPUs, but there are different kinds of GPU models running on the different nodes. So this is also important to note and important to keep in mind when scheduling pods, because different kinds of Spark queries show different kinds of performances on different GPU models. So once you've done that research, it's important to schedule the right pods, which is to say run the right jobs in the right GPU nodes in order to extract the maximum possible benefit from GPUs. So along with node labels, which I just explained, we also have node taints. These can also be used to add certain specifications to a worker node and allow it to be scheduled accordingly. So the next slide, we have the actual running of a Spark job. In our case, we're using a Cloudera data engineering CLI to run this job. However, similar setups also exist on the upstream Spark submit commands. So in this case, as you can see, we've added, there are these two flags, which is the node selector and node toleration added to the executor. So these are added in conjunction to the label and paint that was added in the previous step. And this is helpful again in specifying that this particular job should run on this exact node itself. So we've done this in order to show that, if you know what kind of job you're running, for example, if it's a SQL join or if it's a SQL aggregate, you can specifically schedule it on the node, which is most likely to show you the best benefits here. So now we will go to the demo. So the demo is shown on the Cloudera data platform. So we're looking at the Cloudera data engineering UI here. This setup in the backend has been set up in exactly the same way that Keshav showed us the hierarchical flow diagram of. So with the root with the maximum capacities and then the data engineering part with a certain maximum and guaranteed quotas within it. And now when we run jobs, the pods that get scheduled will request resources from those guaranteed resources within the data engineering queue itself. So let's jump right into the video here. This is what the job interface page of Cloudera data platform looks like. We've already scheduled, configured the jobs. Here you can see that the same node selector that we showed in the CLI step has been added here. And there are certain other flags that are also required by NVIDIA while running jobs on GPU. So now what we'll do is we'll run two jobs. So it's the same job. It's a simple Scala join. We'll run one on a traditional CPU setup and one on the GPU setup, which is represented by job ID 28 and 29 respectively. And we will compare different parameters. So those parameters being the duration that it took to execute and the query plans. So we can see job 28 finished with a duration of 1.1 minutes. So what we'll do now is we'll go into this job, we'll go to the Spark UI, and we'll go to the SQL tab. So this is also available in traditional Spark Submit if you want to try it out. So here, Spark provides us the entire query plan of the job, which is essentially the subqueries that it gets divided into. So you can see here that there will be sequential steps for executing each part of this basic Scala join. So you will see steps such as shuffle, sort, join, and it's a complete hierarchical setup, which then in the end, all of these individual steps come together to execute the main query. So now we'll go back. You can see that job 29, the one which was running on GPU, is also finished. And this finished in a duration of 46 seconds, which in terms of percentages is around a 30% reduction in time. And this is again without any kind of modifications done to the code. This time can even be further reduced by adding even more enhancements. This is the SQL query plan of the GPU running GPU job. And in this case, you'll see that the very first step is a GPU row to columnar in both sides. So what this represents, this is the transfer of memory between the CPU and GPU that takes place. So for the memory to come into GPU and start executing the GPU operations. So now you'll see that every single operation there that was happening on CPU is now happening on GPUs. So that's the query plan, and here there's also a textual description of the same. So you'll see the GPU aggregate, GPU shuffle, GPU sort, etc. operations, which are implying that all of these steps took place on the GPU setup, leading to the performance benefit. Now, I also talked about Spark Rapids being transparent, being a transparent accelerator. And I mentioned that means that it executes successfully on for any job. And you can also see that what operators were be able to execute it on GPU and what still ran on CPU. So if you enable verbose logging in your job, Spark Rapids outputs all that information for you, which is helpful for you to understand how it works and also for you to know how to optimize your jobs even further. So if you see in these logs here, there are certain lines which say that this will run on GPU, like this operator will be executed on GPU. So to say that these were the ones that could be accelerated and were run on GPU by the Rapids plugin. Now there are a few lines which say that this cannot run on GPU because not all expressions cannot be replaced. And then if you see a little 2 lines down, you'll see another line that says that GPU does not currently support this operator class. And then they mention that exact class. So this is the kind of transparent information that's helpful for you to figure out that what part of your current query is not supported on GPU. And then you can easily find alternatives to, replace those queries and even further enhance your jobs and get that time down as much as possible. So that was the demo. And that's also it from our side with respect to this presentation on GPU and Yunicorn. We hope we were able to give you a good intro into the topics, and thank you for your time. And we're happy to take questions if we have any.
Any questions? Thank you very much, Vani and Keshav. That was a fantastic presentation. Vani has something to say.
Thank you so much. It's a very new and Unicorn is something that which I was hearing it the first time. So you've been, my voice is clear.
Loud and clear.
Okay.
So yeah.
You mentioned that you've been using multi-tenant Kubernetes and you're running a Spark workload on the top of that, right?
Yes.
So how you, as it's a multi-tenant, so you're probably splitting up your Kubernetes cluster with a multiple namespace, which is allocating for each and every team. If that is a setup, how you are ensuring that another team content is not being used by other team, and how you are enabling the access for those individual namespaces to, because you are running a high workloads inside it, and it's a data intensive as well as security intensive data. How you are ensuring that one namespace or one team is not accessing other teams without authorization? So how it is happening? Please give some.
So, okay, I'll come to the picture. Yeah, so if you see this, when we partition the cluster, there are some logical groupings and there are some, so these weave nodes is actually representing a namespace. So each of these weave nodes where you define, and you have defined quota like max and guaranteed at each node. And these guys are actually your logical representations. So it's like a team. It's like a team, and this is like the namespace. So and if you wanted further, you could have divided that into dev and prod and all that. So how we are restricting that only so this max is basically restricting that anything that is submitted to this queue is allowed to use up to maximum of 40 GB of RAM. Now, the second question was, how do we ensure that a workload that was supposed to go into this is not being submitted into this? So for that, we have a different solution. I mean, internally, we have something called Cluster Access Manager, which gives you kube configs, which is limited in scope, which and the workloads which are trying to submit into this specific queue will use that specific kube config, and if they try to submit using that kube config to some other Reef nodes, then they will straight away reject that thing. So it's you can manually define it if you want, but you can create those restricted kube configs, and those kube configs will give you the restrictions on who can submit in what queue.
Thank you so much. I like give a follow-up question. So you mentioned that the data ingestion is one team and the data processing is the other team. Those are the two namespaces. Is my understanding right?
Right. These are like the Reef nodes are the namespaces.
Let's say that you started running the pod, which is running on the data ingestion. Let's say that is a 20 gig of pod, right? So the
Right.
pod is trying to do some access to the pod of data processing, which is 80 gig. So how is this get restricted? Is it a free flow access or is it restricted by means of some security policies or the network policies?
Is the question about the process which is running inside this pod, what
Yeah,
it
how
can
you're restricting from accessing from the data processing pod without any authorization?
So we have that in data engineering. So by default, Kubernetes doesn't going to give you. So we have a restriction set in the data engineering. So these data engineering pods are actually trying to access some HDFS data or trying to access something. We have something called base cluster. So they are trying to access Hive, trying to access Kafka, trying to access HDFS. And all of these is controlled via Kerberos. So we automatically mount based on who is logged in. We mount the key tab of that user, and then that key tab grants you access to those resources that this pod is trying to access. So we have boundary authentication, and then from within, once the authentication is done, then we know who you are. But once and then you're trying to do some access on some data which is like where the data is actually. So that is controlled by Kerberos.
Thank you. So you mentioned that the data engineering is a team, right? Is there other namespace or what type of configuration with respect to the Kubernetes?
So data engineering is just a team. If you see the actual configuration of this Yunicorn configs, so it says is parent. So parent is true, then this is not going to create a namespace. But if it is parent is false, then it is going to actually create a namespace. But the limitations that you put, I mean, so you might ask, why not just get rid of this node and just have these namespaces? Why not? But there is another feature called preemption. So that's where this guaranteed max quota comes in. So what happens is in your data ingestion namespace, you have certain resources given, and same is for data processing. Now you have a max here and you have a max here. Guaranteed is 60, but at any point in time, it can go all the way to 70. So how it can go to 70? It has to get it from somewhere. So it will get it from what could have been allocated for data ingestion. It can get that also. But there is a concept called preemption and fencing. So the guaranteed quota that you have, you should be given that quota at any point. So if you're asking for scheduling a pod in this namespace, and that says, I do not have that available because this guy is consuming most of it. So then this will trigger a preemption in this node, this queue, and this queue will, Yunicorn will kick out some of these pods based on sorting algorithm that you have specified in the queue, and then make space for the resources that you are trying to schedule in this queue. And how is this happening is based on the guaranteed. So if your guaranteed quota is not allocated to you, this can trigger a preemption. Now, I can go into more detail. You can have fencing around preemption, fencing around this. So your preemption can happen within that fence. So if I put a fence here and a fence there, then preemption cannot be triggered from data processing to the data ingestion. So how it helps, but if there is no fencing here, it will preempt the pods in this data ingestion queue because there was a fence here and there was no fence here. Now, if you, let's say, divide your data processing into test and prod, you have two teams. So one is just being used for testing stuff and then promoting it to prod in the same cluster. Now, you would like to preempt the pods in the test if needed by a pod in the prod namespace, because but the other way should not happen. And things in the test should not kick out any pod in the prod namespace, because that way you lose the service in the prod. But testing can wait for resources. So that way you put a fence around testing, but not a fence around prod, and prod will be able to kick out something. And so, yeah, there are multiple other features. So if I go, it will take much more time. But I
Thank you
hope
so
that
much.
answers.
Thank you so much. Please, anybody else have any question?
Hi, Keshav. Very elaborate talk. Thank you. So, you mentioned about Yunicorn, right? That's an agnostic scheduler. So,
Right.
how is it different from me labeling all my nodes and then adding taints and tolerations to my workloads? What does it do on top of that?
So, so you taints and toleration and with the existing scheduler. So first limitation is if you put a so taints and toleration is just about you have tainted some nodes and you have some tolerations with you have some pods to tolerate those taints. So that's like selecting some of these nodes. But scheduling is like if in case of default scheduler, even with the existence of taints and toleration, if you schedule a pod and if there are no resources left, then your pod will be rejected right away. And the retry logic has to happen on your side so that you keep retrying until some resources is available. So that's one benefit where Yunicorn will let you queue your resource and you do not have to retry. It will wait, and then when some resources available, it will be able to schedule that to some node, also respecting the taints and toleration. So then the second benefit is your entire Kubernetes cluster is just one queue for your for default scheduler. So yeah, and you can define quotas. I mean, you can define quotas for each of these namespaces, but they are like I said, if there's nothing available, you won't be nothing will wait. You just be rejected if you use the existing quotas. But in case of Yunicorn, you're kind of partitioning your workloads, partitioning your Kubernetes cluster in such a way that each of these teams, like I said, data ingestion and data processing, they can use whatever is max available, but if needed, they can preempt the other guys, and then so you're seeing part of the cluster. So you are seeing, and at the same time, you are allowed to go to a max amount and still be guaranteed some value. So your cluster is not sitting idle in that case. But in case of default scheduler, either you get kicked out, or your cluster is there's a lot of resources waiting for. Sorry, there is a lot of resources in the cluster getting wasted. But this is allowing you to still use the maximum capacity of your cluster all of the time.
Got it. Thanks. So what you're saying is Unicorn scheduler takes into context whatever resource caps you provided here, right?
Yeah. And another thing, it's very well suited for batch workloads. Like I said, so it understands what an application is. That's another way, where gang scheduling comes in. So it understands that your Spark is not just a driver pod. It's a driver pod with a bunch of executors. And if all of them get scheduled at one time, then it is good. Otherwise, it's just a waste of resources for you to just schedule the driver and wait for resources for your executors to come in. So you can define a gang and then say, I want at least 3 executors with the driver to come at once. So that way, so it will wait until those resources are available and then schedule this entire application, which is the driver and the pods,
It's more
sorry,
of
the
all
driver
or
and the executors.
nothing.
So that's another feature.
Anybody else have any other question? Thank you so much. So,
Thank you very much, Keshav and
Okay.
Vani. That was a fantastic talk. And thanks for putting in the time despite the really short window that I gave you. That was a good presentation.
Thank you.
And yeah, thank you everyone. And especially next speaker who gave us a fantastic question. I went into depth. We talked about money and Narasimhan, right? Yeah, thank you. And this is I'd like to hook about the next meetup that I have in line. We have an ML specialist based out of Chennai. Unfortunately, he isn't available today. He's planning about delivering a meetup on how to run your own LLMs locally using Olama as the UI. And it's going to run entirely offline. Like it's not connected to the internet at all. And it's a very good talk. He has already written a blog. I'll share it with you guys. But he's going to deliver a talk soon. It's still in the works. Sometime later this month or probably early next month. It'll be awesome if you can be there and ask more questions. And he is very welcoming when it comes to difficult questions. He's been in the ML space for well over a decade. So he knows, he talks about that stuff. Most of it goes over my head, but sometimes he tells the difference between a transformer model and then other models. So if you are into that stuff, please. If you're not, no problem. He appreciates all sorts of questions. Like he appreciates me asking him dumb questions, so you can put it that way. So I'd like to see you all there for that meetup. I'll hand it over to Manikandan.
thank you so much. Thank you so much for the valuable sessions. So everybody's completed the check-in. So anybody yet to complete the check-in, please connect with Vijay Bharati and Arun for completing the check-in. And if anybody coming for direct registration, please connect with Vijay Bharati for the process. Okay. So we'll go for a 15 minutes break and we'll come back around 11:15. We are on time for the other session, so please please use this opportunity to better network with other people and learn and share. Thank you. Back on now.
Cafeteria is there. We have coffee, samosa.
We have our restrooms with you and direct we have the cafeteria.
In future, okay, like our own meeting. I'll share the link. I want it to be in person.
Oh, you said just.
Yeah.
I don't think
We request everybody to come back to the call. We're going to start the session. So we request everybody to come back to the call. We're going to start the session.
Welcome back. Let's get settled. Yeah, we'll start with the next session. In a couple of minutes.
So it is expected to work very shortly, for a short period. So if you have a design in calculation. This is the guarantee. It exceeds T1.
I guess we can get started. Okay. Okay, for the second session today, we have speaker Lakshmi Narasimhan. He is a full stack developer turned into DevOps engineer. And he is in the field for over 20 years now. And he helps the startups and a lot of enterprise in reducing the time to market. And he helps in following the industry standard and using the Kubernetes tools, the delivery practices. And for the session, integrating machine learning workloads with Kubernetes. So that's the topic for the session. Over to Lakshmi Narasimhan. Thank you, Lakshmi.
Thank you. So people on Zoom can hear me, right? Can you get a bit? Yes. Thank you. So So I assume people are familiar with either Kubernetes or machine learning, or probably both in this audience. Or I can do a quick recap of both. Okay, so machine learning, how we used to do, or we still do, is we spin up a VM. Oh, that's fine. Thank you. We spin up resources in the cloud or on premises, which is optimized for machine learning, like GPUs, like how they said in the previous talk. And then we deploy our models there. Models are pre-trained, artifacts in machine learning, where you train them based on whatever training you give, and then they are deployed in your infrastructure, and then you consume them. You pass some input to the model, and then you get an output based on how you have trained the model. And then based on that inference, you process it further. So this is how a typical machine learning life cycle looks like. You keep on iterating over your models. It's not one and done. You train your models, and then you deploy, and then you create a better version of your model, and then you deploy it. That's how you typically do. The process has not changed much over the years, but the way we do this is enhanced by using the tools which I'm going to talk about right now. So what are the problems we have with the current setup? If we identify them, then it's better to understand and then appreciate how the existing technology solves it. So any questions, please feel free to raise your hands. I'm more of the, in ML ops, I'm more on the ops side and less on the ML side. So ML will be dealing only with the hello world equivalents in this talk. So if you have any ML related deep questions, I'm not the guy. So that's one caveat up front. So the problem with existing conventional ML workloads is they are mostly operated manually by an ops team who don't understand about machine learning, and vice versa. The ML team, they don't know anything about ops typically. So all they care about is my model deployed there? Can I use it? Can I consume it? Can I run my tests? Can I train my model? How do I adjust the tuning parameters and all that? So because of this disconnect, right, we are left a lot of gaps. So one thing is the environment is been up, right? They are inconsistent because it's being managed manually. So I raise an IT ticket typically to spin up a high GPU machine because it's not exactly cheap, right? So they'll take some time to provision it and then give me credentials, and that too, it'll be having very restricted access. And when I'm using a GPU VM, and it's almost always used only for a specific purpose. By the time it is not being used, it is lying idle only because they don't want to spin it up and bring it down based on demand. So that leads to a lot of inefficient resource usage. And the deployment process is very complex, right? It's some DevOps engineer or an ML engineer in conjunction, they wrote some script which is being deployed. Even after that person leaves the job, they still have a very set of pristine scripts which is committed to your Git repo. Nobody knows how to operate it. If something breaks, nobody knows how to fix it. So the deployment process is very complex, to say the least. And there is very limited collaboration because this process is not exactly streamlined, right? There is no way I can share my data or my model across my teams, right? So there is no formal process to do this kind of collaboration. And if I use VMs, right, they involve manual setup and configuration. Now there are tools to spin up VMs, but in spite of that, there is the problem of scaling your VMs, right? If your ML workload is scaling up, all you can do is you can spin up another cloud VM and then scale it horizontally, not vertically. So these are some of the problems which we have in the yeah. So anybody has first-hand experience on this? You run machine learning workloads beyond your laptop in any cloud. So these are some common issues which we face. So for those who don't know what Kubernetes, a quick recap, it's a container orchestration tool. So why do we need container orchestration? Because containers, they are in itself very hard to manage, and then a lot of workloads in normal commodity hardware. But why are we using containers in the first place? They give you all the goodies, right? Like isolation, resource optimal usage, scaling, and all that stuff. So they solve a set of problems, but they bring another set of problems. One among those problems is orchestration. So Kubernetes is a popular orchestrator which will solve these problems. And it brings other good things along with that, not just container orchestration. It brings you scalability. You can scale your workloads based on whatever specification you give. And they are self-healing, meaning if your workload goes down for some reason, Kubernetes maintains a guarantee that it will spin up another container somewhere in the cluster. And then you can issue rolling updates. So if you have a newer version of your application or a machine learning model, you can roll out a new update almost as easy as applying a declarative configuration in your cluster. So these are some of the reasons why we use Kubernetes, but it's not exactly very developer friendly. It's got a steep learning curve and all that. So that's why we have a lot of abstractions and tooling around Kubernetes to solve all these problems, so that you need not have a PhD degree in containers and Kubernetes, but still you want to run some of your workloads. So we have a lot of tooling in the ecosystem around that. Any questions on this? So what is Kubeflow? Kubeflow is a set of tools which will help you run machine learning workloads on Kubernetes. So why do we need a set of tools to run machine learning workloads on Kubernetes? To understand this, we first need to look at what Kubeflow provides, right? So I'll show it from the official. So you can see that I've searched for Kubeflow alternatives yesterday. Yeah, you can see my screen, right? I'll open this image in a new tab probably. So there are two diagrams here. So the first one is the experimental phase and then the production phase. Any machine learning process involves both these phases. The experimental phase is where you're trying to fit a correct model for your problem statement so that you get a good solution. It's not like one and done. So you first collect a lot of data which is pertaining to your problem statement. Like for example, let's take the case of very simple case of identifying handwritten digits, right? So what will be your data in that case? It will be thousands of images with handwritten digits. So you will take all these and then you will train a model based on this input data. In most cases, you will do some processing. You cannot use the data directly. Some data might be bad, some data might be malformed. You might have images. Sometimes even humans can't identify digits which are handwritten in many cases. So we have to sift through this data and then sanitize it before we feed it to a model. And then the way a model learns is it learns like how a kid learns. So for example, you show 10 objects of a ball to a kid and then say this is a ball. So next time you show a 11th object which resembles a ball, the kid is likely to identify it as a ball. So the first phase is the training phase. Second phase is the production phase where you give never before seen a photo of a ball, and then the kid identifies it as a ball or something else. Like if you give a photo of, say, the moon, okay, the kid might identify it as a ball, which is not correct in the strict sense, but something resembling that, right? And then you go back to your experimental phase, and then you tweak your model to say that if I give a photo of a moon, then don't identify it as a ball. Okay? And then you tweak your model, and then that's what the tune the model hyperparameters means. So what that means is your model is nothing but a collection of numerical weights which is deployed. So tuning the model hyperparameters means you're tuning those numbers in such a way that it is more optimal and efficient in at doing the task which it is supposed to do. By the way, any machine learning activity is fine-tuned only to perform a specific task. Nothing is general purpose. So, for example, this model can identify only balls, and so on and so forth. So, once you do that and you're happy with your model, and then you deploy it in a production setting, and then you consume that. For example, from my web application, I'll make an API call to my machine learning model, and then it will respond with an accuracy number, and then saying whether it's a ball, yes or no. So that's how machine learning cycle looks like. So the way we do it with Kubeflow is all these components are swappable in case of Kubeflow. And then I can replace one with another. Like for example, I have multiple machine learning frameworks right here. Maybe I have to point it with the mouse. So Kubeflow gives me an option to choose what ML library I want to use in this phase. And then Kubeflow also gives me an option to choose what kind of experimenting framework I want to use. And then there is a notion called pipeline, which will help me deploy everything and then run it with a set of data. The way we input data to this workflow is also configurable in case of Kubeflow. Everything is deployed in Kubernetes, and then we can tweak everything. So that's the whole idea behind Kubeflow. It is vendor agnostic. It is not maintained by any particular organization, but it is backed strongly by Google. So any questions till now? So we talked about what a typical ML workflow looks like, how we train models and how we serve them, and how we tune the parameters, and then how we manage the pipelines. Very briefly, this is just a 10K feet view of what exactly happens in Kubeflow. But each of these line items is worth a talk in itself. Probably we'll have future sessions on that. So what are the components of Kubeflow? So when I say I have installed Kubeflow, what? Sorry, thank you. So when I say that, hey, I have installed Kubeflow in a Kubernetes cluster. So what? First of all, what are the prerequisites for running Kubeflow? Of course, you should be running Kubernetes. You can be running Kubernetes in any provider, or you can be running it in on-premise also, because Kubeflow provides both these things. And once you're done with your Kubernetes cluster, the next thing is you install some components on top of your cluster to make it useful for Kubeflow. So these involve things like certificate manager, volumes, and then user authentication, and then data management and all that. We'll come to that. And then ultimately the Kubeflow components themselves. So these are the Kubeflow components which are typically installed when you install Kubeflow in a Kubernetes cluster. How you install Kubeflow? Like how you install any other application in Kubernetes, you do a kubectl apply of certain components, right? Same way you can do with Kubeflow. But if you search the internet on how to install Kubeflow for Kubernetes, you will get around 24 approaches. Most of them are obsolete because Kubeflow installation is notoriously hard. There are efforts made to standardize it. In fact, when I was trying to set up Kubeflow, to show a demo for this talk. I spent almost 3 hours in installing Kubeflow, but very less time in actually running the actual ML workload, right? So that is the status quo for Kubeflow installation right now. The closest and the most reliable way to install Kubeflow is using a community script called deploy KF. I'll share the links for that talk. So this typically Kubeflow installs around 20 different components in your cluster. It's very hard to do it by manual approach and then maintain it. So deploy KF comes with a set of clusters, a set of scripts, which will help you deploy and maintain Kubeflow. You can even migrate from, let's say that you're having a previous version of Kubeflow running in your clusters, but you want to migrate to a more streamlined approach. We'll see what exactly is streamlined about this in a couple of minutes. So deploy KF helps you do that also. So this is a very interesting blog post about how Cloudflare is using deploy KF to set up their ML workloads in Kubernetes. So back to Kubeflow components. So there is a central dashboard, which I showed you just now. This is running on a normal VM, which has got 4-core CPU and 16 gigs of RAM. And this is the common dashboard which you have. I will show a demo of it after the talk. So this is a single pane of glass to manage all your Kubeflow artifacts, like your Jupyter notebooks, your pipelines, and all that. And then we have the notebooks themselves. So has anyone not familiar with notebooks, Python notebooks? Please raise hands. You use Jupyter notebooks? No. So a Jupyter notebook is interactive Python program, which is used to create your machine learning model during the experimental phase. So I will show you how it typically looks like in the demo. You don't use it in the production phase, but you use it in the experimental phase. And then we've got pipelines. Pipeline is how you deploy and run your whole machine learning workload in Kubernetes. Kubeflow gives you a first-class component for running a pipeline. And there is something called Katib. Katib is a separate component in your Kubeflow setup, which is used to fine-tune your hyperparameter models. So if you look at the Kubeflow website, they'll have different components which are thoroughly documented. So we talked about central dashboard, and then about Kubeflow notebooks, and then Kubeflow pipelines. So your Katib is your, I don't have Katib installed in this cluster, but this is how it typically looks like. I don't have a UI. So what does it do? It does hyperparameter tuning. Like I mentioned, if you want to tune your ML model is a bunch of weights, numbers. So if you want to tune those parameters, you do it using Katib. These components, they can be installed and managed individually also, but Kubeflow gives you a comprehensive suite of tooling to run this. And then finally, once you have your model ready and deployed, you might want to expose it to your consumers. Otherwise, your machine learning pipeline is of no use. So that's where KServe comes in. KServe was previously known as case serving, but now they changed the name to KServe. So what it does is it's basically a serverless component which will expose your ML model for other consumers to consume it. That's why it's called KServe. This is also a part of your Kubeflow setup. It comes as an external add-on, but you can install it when you are installing Kubeflow. So those are the major components in Kubeflow. Any questions on this? So why should we use Kubeflow, and why not we manage all these tool sets manually? So one thing is they are all updated and scaled efficiently. Like for example, I mentioned about a tool called deploy KF, right? So that is a community maintained thing which will install Kubeflow on your cluster. So you get a one-shot script which will run and then deploy everything in your cluster. I think I have the script run screenshots also here. Yes. So if you see, this is the output of the deploy KF which I ran. So it took about 10 minutes to sync up everything, but ultimately it installed all the cluster artifacts. I'll show you the list of artifacts also which it installed. So this is the reason why we use Kubeflow. You get a lot of battle tested set of tooling and community scripts which work out of the box. You need not do any fine tuning. Of course, it's also possible to install all these tools individually, like I said before, but you'll spend most of your time setting up the whole infrastructure instead of working on the actual ML problem itself. So this is a brief overview of how you set up Kubeflow in your cluster. One is you can directly install all the artifacts, but that is a very, very complicated affair. I tried this and I abandoned this. Nobody recommends this. And then there are a lot of deprecated methods. There was a CLI tool to deploy Kubeflow, but that is deprecated right now. The best option we have right now is deploy KF, which I showed you. So what are some best practices this brings into Kubeflow brings into your cluster? And it actually enforces these so that you need not actually consciously apply these in your workflow. One is it applies the principle of GitOps by default. So anyone not familiar with GitOps? So GitOps is the process of storing your whole infrastructure and artifacts as Git code. The reason why we do it is because we want to have consistent and predictable builds and installations every time. So, for example, if you're deploying an application and then you have all the artifacts stored as a part of your GitHub repo, every time you want to make a change, your Git is the source of truth, and then you go and change the configuration and then do a Git push. It's going to trigger a deployment automatically from that point onwards. The second thing is you have everything written to your GitHub repository. None of this is there in people's head, so that if somebody is not available, they go on a holiday, or if your process is broken, you need not worry about it because it's all there in your Git repo. Git repo acts as a single source of truth. So in the context of Kubeflow, what happens is your ML workload, and then your pipeline, and then your Jupyter notebooks, everything is stored as a part of your Git repository, which I will show you as well. So this is your digit recognizer Kubeflow setup. So you can see that the Kubeflow config for importing the notebook is a YAML file. It's a Kubernetes artifact. So you just have to kubectl apply this, and then you'll get all the notebooks in your cluster. Same way, I have the notebook which can be directly run in your Jupyter notebook, which is deployed in Kubeflow. And then you get the same output. You need not follow some set of instructions. It's already committed to Git. So that's the idea. And then you get multi-tenancy also as a part of your Git flow. Multi-tenancy, right? So what I mean by that is, if I try to step into some other namespace and then try to deploy an ML workload, Kubeflow won't allow me to do that because it has got multi-tenancy rules baked in. So for example, team A has got only access to the notebooks and then the models in this team A's namespace. So they cannot go into team B's namespace and then run their workloads or access their data or anything like that. That's what I mean by multi-tenancy. And you can actually point out which nodes, Kubernetes nodes you want to use for your training and then deployment. I'll show that in a while. Okay, and then you can leverage persistent storage for data. What I mean by that is typically workloads in Kubernetes are ephemeral, which means it's good for running stateless applications. If you remove your workload from the cluster, you use all your data also. But machine learning workloads are typically stateful, right? So Kubeflow helps you preserve the state by storing all the data in persistent volumes. And then we saw that it comes with a component called Kubeflow pipelines. So it helps implement CI/CD pipelines as well. And then obviously your cluster is secure, meaning you don't have access to unauthorized data in a different namespace where you are, first of all, not authorized data. So all these best practices, they come as a part of Kubeflow and they are enforced naturally. You need not make any conscious effort to enforce all these policies in your organization. So I'll just show a brief demo of this. So you can see that my screen is visible, right? Yeah. You can create a new notebook. You can manage all your existing notebooks here. So let's say that I try to create a new notebook in a namespace where I'm not authorized. This has a login logout feature. I'm already logged into this setup. Otherwise, it asks for username password. So let us say that in team1 prod, I try to create a new test. No access. So these are some of the notebook options which I've got. I can use Jupyter, Visual Studio Code, or Studio. And then again, specify what kind of image I want to use. We've got PyTorch, TensorFlow, SciPy. And then what are the CPU RAMs I have to use for this particular notebook. Let's say when I try to launch this, it will say that the user is not authorized to create notebook in the team1 prod namespace. So Kubeflow does this enforcing by default. I need not do anything explicit. So when I look at an existing notebook, right? I can run all my experiments in this without the need for any specialized hardware. So this is the digit recognition thing which I'm running. I just copy the code from here and then I run it. So I get the same output as what I got here. So you can see that. This is the experimental notebook. So I've run till this step. I can run other steps also. Can be used outside the context of Kubeflow also. So what that will do is it is installed as a part of deploy KF. It's one of the prerequisites. So you maintain all these artifacts as Git repos, like I said, and then Argo will actually sync with your Git repo and then update the state of the application according to whatever is there in your Git repo. So you get all the GitOps practices just by installing these tools. You need not do anything exclusive from your end to enforce all these policies. So that's pretty much what I had to show. Any questions? Yeah.
Thank you so much, for the valuable session. So I like to clarify. So you mentioned that the you've been Kubeflows as supporting on persistence volume, right? Generally, the volumes are going by the volume and volume claims. Is it the same method as Kubeflow is trying to use, or how the states is getting persistence?
Kubeflow does that also, but in addition to that, right? For example, if you download a data set from Kaggle, so how many of you are familiar with Kaggle? Kaggle is a machine learning platform. So there you have data sets which are typically running in GB, and then object storage is best suited for machine learning workloads. So persistent volumes are not exactly object storage systems. So in that case, what you do is you store it in an object storage system. You have to deploy it, maintain it. But what Kubeflow does is it comes with its own object storage called Minayo. How many of you are familiar with Minayo? Minayo is the open source equivalent of Amazon S3. So it comes with its own setup of Minayo, which you can, where you can dump your data and then train your model based on that. So you get first class integration for your ML workloads in Kubeflow with Minayo. So that is in addition to the typical persistent volumes which you ship and deploy on a normal Kubernetes cluster. Does that answer your question?
Kubeflow integration is going to be a low cost.
Yes. So if you look at the Kubeflow setup, right? So these are the list of applications and workloads running in my cluster, which I showed right now, to run Kubeflow. So everything is self-contained and minimal. Like for example, I talked about Argo CD. So whatever is there in the kube system namespace, there is staples. It comes with any Kubernetes cluster. And then you have got Argo CD. Argo CD is not associated with Kubeflow, but it helps you enforce GitOps. You can even install Argo CD in a normal cluster. And then you have Cert Manager for managing certificates. And then if you deploy your ML model and expose it, you need TLS certificates that is provided by Cert Manager. Istio is the actual engine which gives you the ingresses and then the rules. Like for example, you want to rate limit your model to so many requests per unit of time. You can enforce all those rules in Istio. Kyverno is a policy engine. Again, it's not exclusive to Kubeflow, but Kubeflow DeployKF wraps all this using other tools like Argo and Kyverno, and then gives you a wholesome developer experience to install it. So all these namespaces which begin with the DeployKF prefix, right? They are value additions provided by DeployKF. For example, Minio, and then auth. Your auth model is DEX-based authentication, which is provided by DeployKF. Your vanilla Kubeflow installation doesn't come with this. You have to set this up on your own. And then whatever is there in the Kubeflow namespace is what ships with Kubeflow. In addition to that, we have a set of custom CRDs. And then just for demo, they have two namespaces, Team 1 and Team 1 Prod. I showed you just now how we are not able to create notebooks in Team 1 Prod because we are a user belonging to Team 1. Okay. So
you deploy it through single Helm chart.
it's not a Helm chart.
You manually.
It's a script actually. So there are artifacts. I don't know why they have not given it as a Helm chart. Probably because Argo CD applications have a lot of interdependent things. So you have to sync them in a particular order only. That's a problem with Argo CD, but that is the best worst thing we have. So.
But when we run Argo CD, it automatically runs its own dependencies.
Yes, it will. One of the prerequisites is you install Argo CD first, and then you run a script which will sync the applications in a particular order. So if you look at this particular run, right, it will prompt me for a set of questions asking, okay, should I do this? Should I do? Yeah, see. It is syncing all these applications one by one. It's a simple shell script which they have provided, which will do all this grunt work. Yeah, you're asking something.
Central dashboard is provided by the deploy KF or
It's from Kubeflow. If you look at their documentation, right, one of their components is the central dashboard. It's not provided by.
KF is applying from the central dashboard.
Exactly. So deploy KF deploys your vanilla Kubeflow components, but that alone doesn't give you a production ready sort of ML infrastructure. You should have some sort of authentication authorization. You should have some sort of policy management. You should have some sort of GitOps, and then some object storage mechanism. So all these additional auxiliary utils, right? They are provided by Plus, if you want to upgrade your Kubeflow to the latest version, doing it manually is a nightmare. So deploy KF makes it a lot easier. There is actually a talk in their website, which was done relatively recently. So that explains the rationale behind why deploy KF was born and how it solves all these problems. This is that talk. I'll probably provide a link to this site.
For enterprise level, so we'll have to deploy KF.
Yes. So if you look at their guide, guys, there are two things: local quick start, and then there is a production quick start also. Saw the link somewhere here. So this explains the idea behind each of the components and dependencies and why they are using what they are using, all that stuff. It's very, in fact, I would say that it is much better documented than Kubeflow itself.
One of the way of running the revolution that I know.
Yes.
Any other thing which you see in the CNCF landscape or open?
I don't know whether this is CNCF landscape. There is a thing called Flight. This is relatively new. A lot of people recommend this over Kubeflow. The reason is Kubeflow's documentation itself is very scanty. So if you search the internet for any Kubeflow Hello World tutorial, right, it's very difficult to find it, and most of it will be outdated. If you try to run that, you will get some API mismatch problems. Plus, the biggest barrier to entry to Kubeflow is you cannot run Kubeflow locally unless you have a super duper machine with a lot of RAM and all that. But Flight, right, it gives you a set of Helm charts. Everything is more cloud native compared to. I've not personally used Flight myself, by the way, but people are saying a lot of good things about that. And it is, again, to Flight. The only thing Kubeflow has going for it is it's backed by Google. So all their internal TensorFlow workloads are managed by Kubeflow.
What is the specification of the server which you are using for it?
For which one? The VM. I can show you that. It's 32 GB RAM, 4-core CPU. 16 GB. 16 GB 4-core. Now I'm not running any workload, so it still occupies around 10% of CPU. So yes, you can spin up a GPU node. You can spin up a cluster with a lot of GPU nodes and then use it. Shouldn't be a problem. In fact, when you try to create a node, right, you can specify a lot of advanced options like only spin up this in nodes which match this particular label or something.
Can you use the existing RO or Simflow or?
Yes, you can. So they have very good documentation around things like if you already have these components, one or more of these components running in a cluster, how you can selectively identify what to install. So even their entire installation procedure is a YAML file. It's an app pattern, or if you're familiar with it. So you can just pick and choose what components you want to install and maintain through their workflow, and then have it.
Hello. Hi. Thanks for the very interesting session. It was very helpful. I have a couple of questions. First is, I understand this, we can use a Kubeflow if you can for a local deployment. How about the the cloud-based ones like GCP, AWS, Azure, like Azure has Azure.
Kubeflow works with any Kubernetes, like I mentioned before. But if you are using any managed Kubernetes, they come with their own distribution of Kubeflow. So you need not sweat over. In fact, you need not even use deploy case. So if you are familiar with Google's Vertex, right? Vertex has a drop-in setup for Kubeflow.
Okay, so if you use GKS or AKS, so they have their own Kubeflow installed.
In fact, if you use Amazon EKS, right, they encourage you to use SageMaker.
Okay. Second question is related to the YAML. So I understand this Kubeflow is helpful for YAML-based deployments and can use in even these cloud vendors. But if you see, if all these three major cloud vendors have their own YAML offerings, like for example, Azure has Azure Machine Learning platform. So can we consider like these are like competing offerings from them, like Azure Machine Learning versus Kubeflow in Azure Kubernetes service?
I answered this question for your previous answer. So they encourage you to use their own machine learning offerings. They don't. If you are saying that, hey, I want to use machine learning in my existing Kubernetes cluster, they'll tell you, no, please use SageMaker or whatever the equivalent is in their cloud offering, because it's good for them, it's good for you also. Under what circumstances would you use something like this? Is you want more control over your ML workflow, which is not possible through their offerings. I don't know to what degree, because like I said, I'm not a pure ML practitioner myself. I'm more on the ops side. So that is what I hear from ML folks. The second thing is, if you are running on-premise Kubernetes, right, all those options are completely ruled out. And most big enterprises like banks, they run their own on-premise Kubernetes. And for them, none of the cloud offerings like Vertex or SageMaker is an option. These are all off the table. So,
in short, my simple question is like, if I am using Azure, if I need to work with the ML models, so which is the recommended? Like, you
go with the cloud offering version.
Azure, like Azure.
Yes, it's the same old question of whether I should. I can actually take a bunch of Azure VMs and then create my own Kubernetes. Okay, what do I have to lose? Why should I use AKS? Right? It's a very tough question to answer because it depends on what you want out of it. If you want to get your hands off managing Kubernetes, updating Kubernetes, and all that stuff, you go with the cloud offered version. If you're okay to do this, if you've got team, if you've got expertise, or for some reason you cannot go with their particular managed Kubernetes, which is very, very unlikely, then you have the option of spinning up normal VMs and then deploying Kubernetes on top of it. There are so many options. Same thing, if you can extend the same argument to something like Kubeflow versus running the Cloud Native ML offering.
Okay, thank you.
Thank you. Thank you.
Thank you, Lakshmi.
We observed that we have around 37 people here. but the checking was happened around of 28 people. We're not sure who has been left out. So if anybody yet to complete the check-in, please connect with Vijay Bharati or Padmanabhan. Because between these lists is required for us. Right?
When you might have got a ticket, if you're not scanned your ticket, please let me know.
Anybody
And
yet
if you
to
don't have
complete the
ticket
check-in?
also, please let me know.
Anybody yet to complete the check-in? Please connect with, I will give you another 5 minutes.
Email set up your system. Set up your system.
Thank you.
Hope everyone has checked in now. Is there anyone left out?
Don't exist on It does not focus on the
Let's give one more minute. Sorry.
their environment is not affected. Whenever you buy three chances, I don't know the option. They know that it's.
Clustering அதெல்லாம் பண்றீங்க அதுக்கும் LLM
Yes, we are back. To start with, how many of you are using Gaggle right now? Fetch the data sets to train. 50, 30. It might be old also, but still. Yeah. Somebody is going to help you with build Gemma, and it is making your Gaggle data set even more mature, fine tuning it. So that's where he's going to help you with. Over to Mani.
Thank you so much. So this talk, we are going to discuss about the Gemma, and I'm going to give some brief about what I learned as a part of the model and showcase some of the use cases that I was learned from. So I'm Manikandan Krishnamurthy. So I've been with IT services for around 15 years and practicing Google Cloud for around 6 years. And I'm generally been an infrastructure architect who build up the entire infrastructure from the network, subnets, and the Kubernetes clusters. I take off. As I see that there is some of the good attractions are happening with respect to the machine learning and LLMs. Started learning about how this thing works, and I was learning how it is being built up, and that is what I was taking some sessions nowadays on the AI and ML LLMs models. If you like to connect with me, you can connect with me on the LinkedIn. And if you have any questions, we used to have a direct interactions. Right. So, how many of you have got opportunity to attend some of our other talks which I was discussing about the build with AI workshop? Anybody attended my previous discussion with respect to build with AI? Could you please raise your hand? Only few people, which is on other community. So GDC Chennai, we've been at a build with AI, so only 2-3 folks. Okay. So this is something like a derivative which I was trying to derive from that particular talk. We are going to discuss about the overview of Gemma and how to access those models and some of the use cases which I feel it is good to share and along that is as a demo. So this is what we are going to discuss about, right? So let's go for the overview. This is my way of representation of what this generative AI is all about and how it differs from the general machine learning models. So in general machine learning, in the general machine learning models, generally whenever we give some data, it is trying to label the data, and whenever we give a data back, it's trying to predict that particular object based on the labels. That is how the general machine learning algorithm works. And what is generative AI is doing the modification. It is understanding the data and it's trained on the data and it does have a capability of generating a data based on the query which we are trying to trigger. This is the primary difference between which I see with respect to generative AI and the general machine learning. So as you guys seen that, I was personally seeing that there's a good number of attraction was happening with respect to generative AI or LLMs. Anybody have thought that why this attraction is very high when it comes for the LLMs or generative AI? Any thought on that? Machine learning and artificial intelligence is there for a long time, right? Around 2016 or 2015. But if you see that the 2024 started picking up the generative AIs and machine learning started picking up, right? So from my understanding, what I observed is it provides the opportunity of flexibility to access the model, which is not early adoption, which is there with respect to the other machine learning or AI. Especially when the ChatGPT comes, it provides the opportunity to access a model in a very easy interface to explore it. Other than the usability, it provides the opportunity to explore it. And other than that, it provides the opportunity, instead of you going and training on your data and waiting long for labeling and waiting some more time to see the outcome of it, somebody has already trained some particular algorithm on the different and their own data or publicly available data. It is readily available for you to use it to see the outcome instead of you trying it. So that is the differentiator I see that the generative AI which is bringing to the table, and it's predominantly it is something like we used to say in our in the infrastructure side, we used to say that
it's going for the MVP. It's trying to provide the minimum viable product in a very short span of time. Whether it's going to be API based or it's going to be whether it's going to be API based or it's going to be accessible via the chat and other interface. That is what I personally see that the adoption of machine learning, adoption of generative AI or LLM is coming in the picture. So before we go for Gemma, let's try to understand let's try to understand the journey of Google as a who's open source the Gemma, who's doing it, and Google, which was doing which is providing a contribution for AI from the long time. It's as per my observation, it starts from around 2015, where AlphaGo, which is trying to compete with the Go playing, right? So anybody started using the AlphaGo 2 server? So AlphaGo 2 is another platform, which the next version of platform which is there, which is trying to provide some DNA-based analysis for the research scientists, which is available for open AlphaGo server, which is available for every researchers. You can go and explore it. That was happened before 2 to 3 months. And then we have a transformer launch, which is another open source, which has been happened around of 2017. And the transformer is one of the breakthrough which has happens on all the machine learning. Even the ChatGPT, whatever I was trying to refer is based on my understanding. Okay. So even the ChatGPT was in turn using a transformer model to do this to do all this research and to do all the machine learning works. And after that, we have a Llama and we have other predictive models for structures and we also have presently we have a Gemini, which is a multimodal which is multimodal, which is available for different aspects like text, image, and the coding. So very brief about the journey. And why I was trying to show this is because Gemma was presently being open source from the Google, and that is primarily I was trying to show with respect to this particular. With respect to Gemini, which is not an open source, which is an enterprise grade of providing a machine learning opportunity to explore the MLN. And this Gemini which comes in like multiple sizes. One is the Flash, which is recently introduced, and we have the Pro, and we have Ultra, and we have the Nano. And how many of you got an opportunity to use Flash? Okay, the Flash is something like which is a faster and less accurate way of doing with the LLMs. And the Pro is already generally available, which is have a mixture of both accuracy, normalization of both accuracy as well as the fastness. Ultra is for the very Ultra is it's not been accessible for everybody. I also don't have access. Anybody seen the Nano, which is coming for Chrome browser? How many of you heard this news? Okay, actually, Nano was the LLM model which has been pretty much going to run on the mobile. You've probably seen that we have something called in Google Photos, right? So you will be cropping some person and it is getting erased, right? So those are something like the machine learning on devices was happening. So those are going to convert into the Gemini Nano and it is going to happen on the device. That is a futuristic. And those are already happening on the Chrome browser. The Chrome browser, which is going to have inbuilt Nano, where you are going to experience this Gemini. So these are something which we've been discussed on my previous talk, and I want to explore the open source model, right? Gemma. So the Gemini is something like it's a commercial component which is from the Google. So Gemma is the open source one. How many of you is already used Gemma? So do you have any other open source LLM you guys seen in the industry? Llama. Llama from Meta, right? Mistral, yes. Mistral CodeWiser, right? CodeWistral. Core Mistral is open source, but not commercially used, I believe. It's not allowed to use a commercial, as per my understanding. So Gemma is a LLM, open source LLM from the Google, and they structured as it is built on the same technology and infrastructure which is used for the Gemini. Right, so Gemma have some different type of variations. The code Gemma, which has been predominantly for code execution and code completion and code generation. The second one is polygemma. So I was referring as a polygemma maybe. So this is something a vision where if you give some image, it's trying to understand the image and trying to extract some information based on your query. And the recurrent gemma is something like a so intensive model, which is specific. You're going to train for specific use case. These are the three variations which I observed. How many of you is already used? If you already use a Gemma, how many of you started using Code Gemma? So these are some of the industrial benchmark which I was taken from those graph, and this have still now there is a comparison with Llama and Llama 2 and Gemma. I'm not finding any direct comparison with respect to Llama 3. It is at most getting equals to other open source model, and there are some benchmark which indicates that it is at most trying to have some resemblance with ChatGPT 3.5. So with respect to Gemma, first thing I was learned for this particular talk, and what I observed is Gemma's accessibles are pretty much happens on the Kaggle. The first thing is you have to submit your consent for consent to the Gemma to get the respective access. And to access the access of model which is available on multiple places. One is Kaggle, and another is as Narayan was mentioned. So we have something like we can access via the Google Vertex AI, and also you can access from the Hugging Face. And these are some of the platform which I was practicing for this particular session. And there are multiple places where you can still get the access to Gemma. And as Gemma is an open source model, whenever you you can get the access for Gemma to run it on your own way. But you should also have enough resource capacity to run it on that. Because when I tried to run it on Kaggle and some other platform, I went into some resource constraints. But you still can use it on other platforms like Colabs and other things. So these are some of the links where you can go for Kaggle to get the access, and where you can go for the once you go there, you will have opportunity to request for the access. So within a few seconds or few minutes, so you're probably getting some consent screen, and once you given your consent, you will get access to the Gemma model. Gemma have different varieties of that. One is 2 billion model and 7 billion models, and we have instruction tune. Multiple things are there, and it is for different use cases. You can choose your own model. But with respect to Code Gemma also, it still have its own variant, but it's instead have a logical connection with the Gemma base model. And once you got the access, you probably get the consent. And so if you want to practice on Kaggle, you can go for this way of getting a consent. And if you're going for Hugging Face, still you need to get the consent. But what I observed from my observation is once you're from the Hugging Face, you're trying to get the consent, this is probably redirecting and trying to connect with Kaggle to complete this particular entire flow. So this access is the first step whenever we want to try to use a model. there are some other places where you can use Gemma without even access or without even the consent, but there is a limited way of discussing, limited way of accessing it. So I hope you got some good understanding about Gemma model. I predominantly started seeing not only Gemma or any of the platform with respect to the use cases, other than how it is being structured. Normally works on the use cases and try to use it in use it in day 1 and day 2 for my work. Okay. Let me showcase of some of the demos which I was seeing. The first thing which I like to, is it audible?
People on the Zoom can't hear you much.
Yes. The first thing which where I feel that we can access it is the chat. If you want to use a chat way of doing it, similar to ChatGPT and other thing, the way you can do it via the Hugging Face / chats. Once you went into, you have opportunity to change the model, and you can have if you see this, you can activate Gemma, and you can start exploring, right? So now we have activated the Gemma model, and you can ask about. So you have some examples, you can use that. Or if you want to put your own questions, like if you want to have your own questions, which is creating some Fibonacci series. I was using the same question which I was used. And you can use, this is the easiest way of exploring the Gemma model. And this is the one place which I want, this is right. Other than that, so if you want to explore the polygemma, I see in this space is very good to explore the polygemma. So example, there are some, I was trying to go with this one. So let me pick up this one. It is something like if you're going to give the image and it is going to provide you some produce the outcome of this image. So there are some people who is already using it. And this is speaks about the default one. It is speaks about the how many red balls is there, and it's trying to recognize the number of balls, and it is trying to refer, right? And there are some errors which I see. Maybe there are some errors which I see. Maybe the next version which is provides updated one, that Gemma 2, but presently this poly Gemma was not running on Gemma 2. And it is some of the time it shows error, but we can see that it is trying to, even though it's an open source model, it's trying to provide some near results. And there are some good number of use cases which is being listed here. These are the place which I see that you can explore the Gemma models. So we've seen that how we can use the Gemma or the chat, and also we've seen that how we can use it on the use some polygemma. So with a very good number of spaces is already getting created on the Gemma model, and you can also explore by means of this link. So let us go and see for some other way where we can take this Gemma model and we can run it on the notebooks. Right. So first thing, we need to complete the access for the Gemma. So once you complete the access for Gemma, you should be have opportunity to run the Gemma in a different way. So this is the Kaggle's Gemma page where you have multiple variant where you can run it via the transformer model, Keras model, and you can have multiple variation, and each one have its own variant of 2 billion parameter instruction tune model. So I've taken all the samples and just trying to practice and put together. It will have some time, some errors and other things, but let's try it. So whenever you want to try to run the Gemma model, the first preferred way is you have to run it on the GPUs and not the CPUs. And the GPU which is trying to provide me the opportunity to run this Gemma model is T4. And I don't have access to other models, but if you have access to other run times, you can pretty much try to check it. Okay. So first thing, let's try. I have two use cases where one use case where I'm going to use a Gemma model and going to use a Keras and then running the Gemma model as a text-based one. And the other demo which I have it on using a code Gemma and trying to see some code generation. Initially, we need to have and the notebook parameters gets load, and after that we are going to have the Kaggle figure which gets tagged on the notebooks, and then we are going to install and enable the Keras model, and then we are going to try see how the Gemma was trying to reproduce. Cannot run the two notebooks at the same time. It will show some errors and other things. These are demos which I was taken from this. You try to see if you want to run this particular code demo. You probably see the examples here. I see most of the examples are working as per the code, but some of the examples not working, especially when it's crossed the memory limits. So my demo is predominantly showcase, we have opportunity to explore the Gemma model in your own notebooks and in your own interfaces. So with respect to Keras model, I was able to run on the Gemma model on Gemma model with respect to Keras NLP, but with respect to the notebook, with respect to Code Gemma is not running for me, at least on Keras NLP. So for that, I was using a transformer model, and when the things gets loaded, let's try to see the difference of that. With respect to the transformer model, we able to allocate, we have to use a transformer, and then we can use a pre-trained model of Gemma, and with respect to 1.12 billion. There are some multiple pre-trained models are available. This is the one which is provides me the response. So I already ran some outcome, and I then been captured. And when I try to ask for the function to calculate the Fibonacci one, which is runs on the local. And one more thing is, both of the places we are running on the local on the notebook, and we are not running anywhere on the cloud or somewhere else. Those are getting downloaded on the notebook, and your machine is just getting created for this particular notebook for this particular runtime, which gets triggered, and everything is data are stored on the notebook, and your data are not going out of it. Right. So if you see, it is generating the Fibonacci series. For some reason, we need to give some more parameter because we see that the generation was happening 2 times. So we have the same function which gets repeats below, right? It's generating for twice. That is happens for any other
any other query which we are giving. So even if you try to give, try to generate a personal professional page, and it is getting timed out when it's crossing the memory limit. So I'm not pretty sure is it getting timed out. I'm not pretty sure whether it's getting timed out because of I was running a 2 notebook and it's crossing the limit. And some of the time the codes are not getting completed properly, but there are some good number of parameters which can be used to fine tune it. So now I was calling the Gemma model, and on this particular notebook. So now I'm giving the prompt to this particular model. Something like a what is LLM? And it is giving me the results. I was just printing the results from that. So in this way, we can access the model and you can run it on your own notebooks and other things. And with respect to the code Gemma, which is predominantly for me, it is not running with respect to Kaggle. And I try to fetch it, it just shows that it has some error and it is not running. Right? Not sure that I can do that. So for that, I use the transformer model to explore the. But what I observed is pretty much it is giving the results, but it is not fully accurate and it has some error. But whenever this type of open source model actually comes in a place when you try to do the productionized application. Because these are going to come with the default license where you can use it for your own production application, which can be used for commercial. But there are some models which cannot be used as a conflict of interest. If example, if you're going to try give the product, which is going to have the conflict of interest with the product, which is already which is the source of that, right? So those have some conflict of interest, but not all the models. So whenever you are using ChatGPT and other models, you also I recommend you also try with the open source model because that is what the history indicates. We had a Microsoft and we have the Microsoft Office and we have a Libra Open Office and LibreOffice. And we also, with respect to orchestration, we have the Docker Span, I believe, and we had a Kubernetes. The open source Kubernetes has taken over of the Docker Span. I don't think anybody using a Docker Spans now. Similarly, it is expected to happen for the, I believe it's expected to happen for LLM. The going forward is going to be the open source model, which is expected to take care. The only thing which somebody may already working on it, something to be solved is how to run the model. Because with respect to previous open source or previous kind of thing, you can run it on your own system and you can explore. But with respect to LLM models, it's not easily ready to run it on your local machines. But there are some of the companies just already offering it, something like NVIDIA's and other companies which is already offering. This notebook also is one of the things. If you already coming with the T4 GPU, T4, I believe it is a Tesla T4, I believe. Right. So even now you're going giving the opportunity to deploy when you send the prompt and it is getting opportunity to you see the outcome. But one more thing is if you want to run it on the production application, you can probably run it on the Vertex AI. Google Cloud Vertex AI is providing some quota where you can explore and deploy this model. The reason I was used a transformer instead of Keras, I was not receiving the output for that
probably when any expert ML developers can try working on cracking that particular code. So these are some of the ways where you can go for Hugging Face chat to explore Gemma. And we have a Kaggle, but Kaggle notebooks, this particular Gemma model is not running or not giving me the outcome. And Colab is pretty much you're able to see the outcome. So that is what I prepared for this particular today's talk. And I take this opportunity to thank the GD who has been inspired me on the Getting Started guide. This presentation has been derived from the Getting Started guide, which is provided with one of the GDs. And if you like to follow me on the LinkedIn, you can follow me here. And if you have any questions, just let me know.